Hey everyone, let's get started. Good morning. So on Thursday we'll be in the lab to give you some time to work on the lab one or project one. Both TAs will be in there. Soyash, do you guys remember Soyash from 611? He'll be there, and Alex. I will not because I'll be serving on an NSF panel on Thursday and Friday. But we'll have two TAs in there. Okay, so last week we had a quiz. I was going to go over that real fast to make sure everyone's clear on that. That had a question: what's the size of a peripheral's I/O space whose address begins at 1100 in hex and ends at address 2 CEF at hex in hex? So you subtract in hex, convert to base 10, convert the difference to base 10, which is 1 BEF. In hex is 7,152 in base 10 in decimal. And then you want to add 1 because it's an inclusive range. Okay. Any questions? Suppose variable b contains the value 1, 2, 3, 4 in hex. To what value will it change after executing code b equals b or 1 shifted by 5 bits to the left? So that would just turn on bit 5 if it was currently turned off. Otherwise, it has no effect at all. So in this case, 1, 2, 3, 4 already has bit 5 set, right? So the 3 corresponds to bit 7 down to 4, right? And then so bits 4 and 5 would be on, corresponding to the value 3. Okay, suppose variable 3 contains a value 1, 2, 3, 4. To what value will it change after executing code b equals, or whatever, that code. So that one's more complicated. You have to figure this out by determining the order of operations. So 1 shifted by 5 bits to the left, subtracting 1 gives you 5 1 bits. So that is this part of the code. Gives us 5 1 bits. And then you have that 5 1 bits and you shift that 1 bit to the left. So you still have 5 1 bits, 5 bits turned on, but now you've shifted it 1 bit to the left. So, you still have 5 1 bits, but now you have a 0 here on the right-hand side. And then we're doing an AND. So we're bit masking. So that's just going to pass, it's going to leave bits, what would this be? 5 down to 1. This is bits 5 down to 1. So whatever B had in bits 5 down to 1 will be retained, and everything else will be masked off. Okay, so the question is for 1, 2, 3, 4, what does that mean? So let's see, bits, so that will, in the case of this, let's see, 4 is 0, 1, 0, 0, and so you've got a 1 there that's going to be corresponding to this bit, right? So that should be left alone. So 4 will be retained, and then the 3 in this hex digit is 0, 0, 1, 1. That corresponds to bits 5 and 4, and those will be retained. So that digit 3 will be retained, but then the 1, 2 in the upper 8 bits will be both turned off. Does it make sense? Because 1 and 2 is spanning bit position bits 15 rather, down to bit 8, right? And so, those will be masked off. Does that make sense? If you have any questions, let me know. I'm going through these fast. I think everyone's comfortable with this. Suppose you want to set bit 3 in the variable b to 0. What line of code will accomplish this? So there's a few options here. You want to set bit 3 to 0. Right. So that first one is basically just turning off bit 0 and shifting the whole result of that to the left, right? That doesn't work, right? This one just turns on bit 3, so that doesn't work. This one turns on all bits except for bit 3. Why does it turn on and not mask? Because it's an OR. There's an OR here. And this one is doing the bit mask operation. So this one turns off bit 3, right? So the answer is D, right? Oh, we want to, yeah, set it to 0. So yeah, answer is D. Setting a bit to 0 is same as turning it off, right? Okay, suppose there is a 32-bit variable named iostat containing the bit field 4 down to 2 that you need to read. What expression will accomplish this? This one will give us 5 1 bits, 1 shifted by 5 to the left, subtract 1. And so this will mask off the lower 5 bits. Okay? Now you might say, well, that's no good. Well, actually, that's not bad. I mean, we want bits 4 down to 2, right? So 4, 3, 2, 1, 0 is 5 bits, right? So we're masking off the lower 5 bits. We want 4 down to 2, so we want some of the lower 5 bits, right? We just don't want bits 1 down to 0. So then this guy will take the result of that and shift it 2 bits to the right, which will end up, that'll give us what we want. It'll give us bits, so it'll shift off bits 1 down to 0 here. It will retain bits 4 down to 2, and it right justifies it. Make sense? Okay. All right, and then there was another one here. This one was kind of crazy. So option B was where you took iostat and shifted it 27 bits to the left. What does that do? So this one is kind of confusing. So we want bits 4 down to 2. If you shift 27 bits to the left, you end up adding 4 to 27, meaning that the original bit position 4 is going to be in bit position 31 after you do that shift. And then we subsequently take the result of that and shift it 29 bits back to the right, which will, 29, right? Which will essentially take these 3 bits that are on the left and shift them to the right. So it'll right justify it, right? So that also accomplishes the same thing, that isolates those three bits. And then this one shifts iostat 2 bits to the right, masks by 7. That also works. So the answer is all of those. They all do the same thing. They're all equivalent. I think. Well, there's another option here. This one is masking off 3 bits and shifting the result to the right by 2, which is, I think, pretty much the same as this, right? Because, right, 1 shifted by 3 bits is 8. You subtract 1 is 7. So, yeah. Makes sense? All right. Which of the following bit sequences show a pulse width modulation signal with a duty cycle of 2 and a period of 5? So this is showing these in binary. So duty cycle 2, which means you're going to have out of every 5 units of time, 2 units are 1, right? So that matches this first guy here, right? You've got this 11000, 11000, so this is repeated twice. So there's 5 bits and 2 bits are 1. Make sense? Question?
How frequent are going to be the quizzes?
I give them every 1 or 2 weeks. I was planning to give the next one next week.
Yeah, it was just I did it again. I forgot.
Okay. Yeah, it's yeah. The quizzes are, I forget what their weights are. They're not weighted that highly.
Okay, maybe like 2.5%.
Something like that. Yeah. Yes. Okay, assume a peripheral can raise an interrupt every 20 milliseconds. What's the maximum possible interrupt rate? So pretty much just, the reciprocal of that. So 50 interrupts per second, 1 divided by 0.02. All right, any questions? All right, so let's go back to the material. So last time I got through SPI. See, I talked about interrupts, and we talked about SPI. Okay, so we got through the 4 timing modes. Then we talked about how SPI is built on the concept of exchanges, where you're exchanging bits between the master and slave. And I mentioned that that's not something that you typically need to do, assuming you're using some sort of transactional protocol, like a programmed I/O type thing, where you're reading and writing registers. So SPI is kind of wasteful in the sense that it supports this bidirectionality, this true bidirectionality where data bits are flowing in both directions. It's not really needed. And so you have to be aware of the terminology, and this still trips me up, but an exchange is like the lowest level of the SPI protocol. It defines this notion of exchanging data between the master and slave. And then you've got a transaction, which is a protocol that's built on top of that. And it allows you to turn this exchange process into a protocol by which you can read and write addresses, which is typically how SPI, at least in my experience, I mean, I'm sure there's a lot of ways that SPI has been used. But in my experience with the types of chips we're using in this class, they typically want to use a transactional type programmed I/O style. And when I say programmed I/O, what I really mean by that? Programmed I/O is defined as having an address. It's an addressable transaction. When I was a kid, they used to call it a coordinate addressable memory, meaning that there's an address and then there's data. SPI, the protocol of SPI doesn't really have a concept of an address at all. So the transaction protocol is built on top of this exchange protocol. So when you read, you have to have at least 2 transactions. So the simplest form of this is in the first transaction, you send the address over, and in the second transaction, you send the data back. So in the first transaction, only MOSI is being used, and in the second transaction, sorry, see, I screwed it up again. In the first exchange, only MOSI is used. In the second exchange, only MISO is used, right? So you're only using half the bandwidth of the channel here, because you're only using one of the 2 data bits, data lines, data pins at a time. So the first exchange is, you can think of that like a header, like a network header almost, where you send the header, which is the address, and then the second exchange is the data, and that data is either going to go from the master to slave if it's a write, or from the slave back to the master if it's a read. Okay, so that's the transaction protocol, or one possible transaction protocol. There's, you can do this in different ways. So this shows an example of that. And then there's the write. Okay, so in order to solve one of these waveforms, if I give you one of these waveforms, there's a few things you have to be aware of. The first is you got to know when to. So the biggest issue here is that I mentioned there's 2 exchanges, right? Each exchange is 8 bits, so there's 16 cycles here. Does that look like 16 cycles to you? Kind of, but it's really hard to see where the cycles are here, right? Which is why I added these, I added these dotted lines. I mean, there are dotted lines on there already, but you need some way to be able to figure out what's going on in each cycle. And so this is when the timing mode matters. You want to know when you should be reading that data. So in this case, CIFA is 1, which means you're going to start reading on the second edge of the clock. So there's the second edge of the clock, there's the first, there's the second. So I drew these lines on the first edge of the clock, starting with the first edge, because the idea was I was going to read the data in between these dotted lines. Now you could also think of it as saying, well, why don't I read it on the black dotted line, or in between, or you could say in between the red dotted lines or on the black dotted line, right? So once you've got that straight, then you have to just translate, you have to convert this plot to bits. And so you're either high or low, and so you translate these to bits. And assuming this is generated correctly, and assuming this transaction is comprised of two exchanges, there should be 16 bits on MOSI and 16 bits on MISO. And then once you have the MOSI bits in the first exchange, you can convert that into whatever those bits mean. Like you can interpret the header, right, which is the address and whether you're reading or writing. And in some cases, whether you're doing a streaming or a you know, like a multiple data or single data, right? But that depends on what those bits mean. And so, do we know? I don't know. I don't remember. Which bit is which in there? Yeah. So the read or write bit in this case is the first one, the most significant bit of the header. And then we have DC. DC is don't care, I assume, right? We don't care about these bits because the address is only 5 bits. So there's a 5-bit address contained within the 8-bit header. A 6-bit is the read or write, which means we have 2 bits left over that are don't cares in this case. But again, this encoding depends on the application. So you have to read the data sheet. In other words, what I'm trying to say is that the hardware, the ESP32 hardware only knows how to do exchanges. It doesn't know how to do transactions. The transactional behavior is part of the driver, essentially, in the software. It's determined by the software. So this is a software behavior. The transaction is a software behavior. The exchange is part of the hardware behavior, unless you're bit banging. Unless you're writing bit bang code, which is where the software individually controls the bits. But in the ESP32, there's SPI hardware, right?
Yeah.
Yeah. How many channels do you know?
I am not sure, but at least 2, maybe 3.
Yeah.
Maybe more than that.
So you're limited. So when you use hardware SPI, you're limited to however many physical SPI interfaces are on your chip, and different chips have different numbers. I think even the Raspberry Pi has SPI, hardware SPI, right?
I think so, yeah. One of them on the
Yeah.
ESP is dedicated to the SPI flash, so you can't really use that one for anything else. But I think there are 2 others that you can actually use.
Oh, okay. Okay, yeah. So that's a good point too. So flash memory uses SPI, right? Seems like a bad choice because, as I mentioned, SPI is not really set up for reads and writes of addresses. So why would you use that for flash? It's not a very efficient way. But yeah, it turns out flash is typically interfaced with SPI.
And it uses like quad SPI, so you have 4 data lines, so you got parallel
Oh, yeah.
communication. So
Oh,
it's
right,
like
right.
a modification of the standard once again.
Yeah. Yeah. So if you want more bandwidth, you can have multiple channels, multiple lanes. Okay. All right. Any questions about that? Is everyone clear on that? So that's all just review. I covered all that already. Then I mentioned you can have, you don't necessarily want to have to send one address for every data word. Why not have a case where if you want to read multiple data words or write multiple data words, you could just send one address for that, the starting address. And that's what this streaming or multi-mode is designed to do. So again, though, this is a protocol that's defined by the application. So if you're going to do streaming, there's different ways to do that depending on how it's implemented. In this case, I have the multiple and single bit is in bit 6 of the header. But when you do lab 1, we do it differently in lab 1. So in lab 1, we have a protocol that's a little different than that. In that case, we have our address bits in the upper bits, the bits 7 down to 2, we have our read or write bit is bit 1, and our single and stream is in bit 0. And if you do a stream, the second exchange, always screw that up, I got it though, second exchange, which is the second 8 bits, is used to specify the length of the stream length, which is not shown here because this is not a streaming one. Yeah, this is a streaming one. So this is a streaming read, and so the first 2 exchanges, the first 2 bytes, are basically part of the header sent by the master. The first contains the address, the second one contains the stream length, and then the subsequent ones are the data. So in this case, we're doing a stream of 2. We're reading 2 words, 2 bytes from the slave, and so that requires 4 exchanges, or 4 times 8, which is 32 cycles, right? It takes 32 cycles to do that. Make sense? Okay, so in lab 1, you're just going to be, reading the trace, reading what's going on in the waveform, and decoding that. In this case, your program should print read stream, and then 24, which is the address, and then the 2 values that we read, which was F and B. Right? Now keep in mind that one of the challenges in your code is, in order to determine what the data is, you're going to get the data either from MISO or MOSI, depending on whether it's a read or write. So as you're decoding this protocol, your program has to be aware of whether this is a read or write, and will read these values from a different signal depending on if it's a read or write. You guys with me? Which in your code is just an if statement. It's not that complicated, but you have to explicitly deal with that. Okay. All right. So that was now that was the lab 1. We'll be in lab on Thursday to work on that. Multi-SPI. So SPI single master per channel. So as Alex said, if you have an ESP32 and you have two channels, 2 SPI interfaces, then you have like 2 master ports on that chip. So that chip could take mastership of 2 buses or 2 channels. The question is, how many slaves can you have? Generally just 1, usually just 1. So typically SPI is a point-to-point, you just have 2 ends of the connection. However, I've heard of ways that you can have multiple slaves. I've heard of this. I've never seen it done, ever. But the rumor is that you can have multiple slaves, and there's a few ways to do that, in theory. One way is you can take the clock, MOSI, and MISO, and those can be shared by all the slaves. But then you can have separate slave selects for each one. So this is going to require multiple slave selects, which will basically, remember I said at the beginning of this that SPI is a 4-wire channel, but this is not 4 wires, this is 6 wires, right? So I need 6 wires if I want to use this approach to have 3 different slaves. Okay, that's one way to do it. Another way is, this one's a little cooler, I think, but the performance is lower. You can do daisy chaining, which is where, if you look at the first slave, instead of sending MISO directly back to the master, as you typically do, you have MOSI goes to the slave, MISO comes back to the master. You can, instead of doing that, you can have the first slave connect its MISO down to the MOSI of the next slave, right? So you can create a chain of these things. And then likewise, the second slave has MISO connects to the MOSI of the third slave, and this third slave's MISO goes back to the master, right? So in order for this to work, in this case, you only need to have 1 slave select. But in order for that to work, if I want to do 1 exchange, it's no longer 8 cycles per byte. It's going to be, how many? 24 cycles, right? Because I have to cycle those 8 bits through all 3. So I have to multiply. It's 8 times 3 cycles, right? So that's another option. However, there's a weird subtlety with this first approach. The problem here is that if you have clock and MOSI and you fan them out, you take the same clock and the same MOSI and you connect it to all 3 slaves. All 3 slaves are going to see the same signal state on clock and MOSI, right? But there's a problem here with MISO. Because in the case of clock and MOSI, you have one entity that's setting those, and then you're broadcasting those values out to three endpoints. But MISO has a problem because this one has a fan in, not a fan out, meaning that I've got 3 entities that can set MISO, and all 3 of these guys are shorted together to one signal that goes back into the master, right? So that's kind of an issue, right? Because notice there's no mux here or anything that's facilitating this. They're just shorted, right? These mesos are just shorted together, right? So yeah, so that's a problem which I am going to return to when we talk about I squared C. So keep that in mind. We'll come back to that. Okay, so then just to finish up reviewing though, UART, we started talking about UART last time. UART is also a point-to-point. Generally, there's just 2 entities that participate in a UART channel. It's just basically, it's also bidirectional, which is equally as pointless as it is in SPI, because generally you're not doing bidirectional with UART. I mean, sometimes I'm sure there's cases where you can, but I think in most commonly you're not. But you have a transmit on one end that's going to be connected to the receive on the other, and vice versa. So in order for this to work, it's not like SPI where you connect MOSI on one side to MOSI on the other, and MISO on one side to MISO on the other. The connections are made based on the names, so you match name for name, right? Each side of the connection has connections that are made by the names, right? The matching names. You match up the pins. You don't do that with UART, because with UART, you have to connect the transmit on one side to the receive on the other. So the signal name, the pin name on here, is not the same as the pin name here, unlike in SPI where the pin names match, right? So this is sometimes called it's a crossover or a null modem connection, I think, typically. If you get that wrong when you're, wiring up your breadboard or making your circuit board, then that's going to be that's a pretty serious problem. And then I showed there's a ground connection too, which is kind of redundant because there's also a ground in SPI too. I just didn't show it. So you'll notice that there's no slave select and there's no clock. So there's no clock because this is an asynchronous. It's asynchronous. There's no clock, and there's no slave select because instead of using slave select, it uses this concept of start and stop bits. So in UART, the channel is held at logic 1 normally when it's idle. And then when you want to use the channel, when you want to transmit data, you pull it down to 0 for 1 cycle. Now, what is a cycle? If there's no clock, how could you possibly know what a cycle is? Because both sides of the channel have to pre-agree on the cycle time, the bit time, right? When I say the clock period, right? Which is called the baud rate. So you pre-agree on a baud rate, and then the reciprocal of the baud rate is the bit time. That's how much time is allocated to each bit time on the channel. The problem with that is that it doesn't make any guarantees about the phase. It's only talking about the bit time, right? So the issue that you have with UART is that I know how much time is set aside for each bit on the receiving end, but I don't know when the transmitter is changing those bits. I don't know when I'm supposed to sample it, right? Which causes errors, inevitably causes errors. There's just no way around it. You're going to get errors. So keep that in mind. But the start bit is when you pull down the channel, the bit for one bit time, and then you just send the bits in consecutive cycles. And they have to be consecutive cycles according to the baud rate of the channel. The problem is, how many bits do you send, and are you sending most significant bit first or least significant bit first? Well, that depends on the settings of the channel. So typically, you'll have 8 bits, data bits. That's the most common case, but that doesn't have to be the case. You can have more than one. You could have more or less than 8 bits, but generally speaking, it's 8. And then when you're done sending, you would just have a stop bit or stop bits. You can have more than one stop bit where the channel just goes high. So basically what the stop bit does is it guarantees that if you're sending consecutive words or consecutive bytes, you know that you're going to have a falling edge for the start bit, right? So the idea is that the purpose of the stop bit is to reset the channel, get that data high, so then I can wait for it to go low to signify the start bit, right? Does that make sense? Now, you can have more than one stop bit, and if you have more than one stop bit, all that does is it spaces out consecutive transactions more, right? So typically you'll have one stop bit, and that just guarantees that there's at least one bit time of separation, actually 2 if you include the start bit, between consecutive values being sent. Does that make sense? So the purpose of this is to reset the wire and to space apart consecutive transactions. Okay, so that's UART. Okay, and then we have an option for having a parity as well. So I mentioned that because there's no information about clock phase, there's a chance that the driver will be changing the bit while the receiver is reading it, and that can lead to a metastability condition. It's unlikely when the speed is low, and UART is low speed compared to SPI, usually. But the parity bit is designed to be able to detect and detect if there's an error. Okay, so if you have a parity bit, these guys have parity. Okay, so if you have a parity bit, it comes right after the data, the last data bit. And it's a little confusing because you can have even parity or odd parity. And even parity refers to, parity is like the number of ones, right? Now, you questioned?
Yeah, I was just curious.
I'm sorry, what was it again?
What's its use case? If it's
Yeah, so UART is used for, usually used for terminals, like printing. But as Alex mentioned, it's also used, wow, that's awful. I assume that's on the 3rd floor, right? Huh?
Sounds like it's like right through that wall. Yeah.
Can you go check for me? And if they're in there working, can you tell them to give us a break?
Sure.
Thank you. Yes. Sorry?
You said last election that the market was used for.
Yeah. So they use it for. So UART is also used for interfacing components, like in drones, and which, I guess the idea there is that with UART, you can define a protocol based on ASCII text. You can make it like, you could define a set of commands, like almost like almost like human readable. Were they over there?
If it isn't there, I can't get in. I knocked on the door. It's like a mechanical room. I knocked on the door, nobody answered.
Okay.
It's locked. So if it is over there, I can't do anything. If
Okay.
you want me to check the third floor, I can check over there too.
Yeah, it sounds to me like it's coming from above, but
I can look up there.
I appreciate it. So UART, with UART, you can have a protocol that's kind of human, like that sends like text essentially, right? And so some drones will actually do that. You'll have a text-based interface where the flight controller can send commands to the drone, or or to any kind of robotic type application, and just tell it what to do in ASCII essentially. Like, so you could say, like, literally print a string. Like, in other words, you do communication by way of strings, right? ASCII strings. So that, I think that makes it a little easier to interface, because I think UART is more common as a protocol than SPI, especially if you have a really low cost chip. But I don't know the whole history of it. But yeah, I mean, it's, in my experience, I usually use it as a terminal. But like I said, and also, I guess, Arduinos are programmed over. You actually send the code through, the program code through UART, which I think the reason for that is because when you have a USB connection to like a single board computer, like did you find them?
Same deal out there. Mechanical room. I knocked on the door. Nobody answered. There's no apparent instruction anywhere else. So
Okay.
seems like they stopped for now, but.
So to answer your question, when you program the Arduino, you're programming it generally from a PC over USB, and you can do UART over USB, right? I don't think you can do SPI over USB, right? I don't think so, right? That's not a thing, right? So if you want to program your Arduino, UART is an obvious choice, because there's like built-in support for UART over USB, right? Does that make sense?
Yeah.
Now, if you're doing UART over USB, I don't know if it's using exactly the same protocol. It's taking the UART and encapsulating inside of USB packets, right? This timing diagram is assuming you just have straight UART, right? This is not UART over USB, right? USB is like a packet-based protocol, right? Where you would be bundling these messages over packets. In that case, you're kind of emulating UART. You're not directly implementing UART signal-wise. All right. Okay. So I have some examples here of some UART. These are a little bit misleading, though, because I wrote this software that generates these timing diagrams. But it was originally designed for SPI, which means that when you look at this, the transmit and the receive are aligned perfectly. Like you're doing one transmit and one receive simultaneously, which is not realistic, because usually you're doing a transmit or a receive. You don't necessarily do them both at the same time like you do with SPI. So these timing diagrams are a little bit misleading because they show the transmit and the receive happening at the same time. But in this case, it says, what bytes are exchanged. So in order to figure this out, you look at the first byte, and you look at the first bit time, and you can see that the first bit time is low. That's meant to show the start bit, right? That's the start bit, and then you have to count. In this case, there's 7 data bits, so I have to count 7. 1, 2, 3, 4, 5, 6, 7. So there's my data bits. And then there's 2 stop bits, and you can see that the 2 bits at the end are high, meaning that's a stop sequence. And so now I'm trying to, the bits sent on UART, I have it shown here as least significant bit first. Is that generally how it's sent, or is that an optional thing?
I think you can switch it, but I think it is generally at least.
Yeah, I think that's how I remember it too. So generally, it's most often the case that the bits, when they're sent, are sent from right to left, not left to right. They're sent least significant. So in this case, I have to look at these bits, and then the bit I'm sending is or the bit I'm receiving. Is that what it's asking? What bits? Yeah, oh, sorry, over here. The bit I'm sending is 0, 0, 0. Okay, remember there's 7 bits, so I'm going to count 3 bits, 0, 0, 0, and then 4. Oh, actually, no, that's not right. That doesn't matter because they're reversed. So 0, 0, 0, 0, 0, 0, 1, 1, right? So that's 0, 0, 0, 0, 0, 0, 1. So 6 zeros and 1, 1. But then, if I want to interpret those, I have to reverse the order because it was least significant bit first. So in reality, the data was 1 followed by 6 zeros, not 6 zeros followed by 1, right? So that's, I think SPI is usually most significant bit first, right? Typically?
Yeah, typically.
So, and typically, UART is least significant bit first. So you don't have to reverse the data bits in SPI, but you do in UART, right?
And that's one of the things, like in UART, parity, start bits, stop, or not start bits, but parity, stop bits, and data bits, those are the things you change like all the time. Those vary like between like every UART communication. But the bit order, least significant versus most significant, that is not something you're going to change very often. It's pretty much always least significant.
Yeah.
Occasionally it can be most significant, but that's not something you change very often compared to the other parameters.
Yeah, these parameters, again, these are, as long as you're matching on both sides, you have to make sure they're matched on both sides. And like I said, usually the peripheral, they're going to be hard-coded, so the controller, the microcontroller side is where you have to make sure that you're obeying the parameters of the peripheral that you're talking to. Okay, so this did not have parity. So let me get back to parity here. I started talking about that. All right, so let me go back here. So parity. So parity refers to number. It's referring to the number of 1 bits. And so an even parity means there's an even number of 1 bits, and an odd parity means there's an odd number of 1 bits, right? But here's the catch here. This is what makes this confusing in UART. When you do your parity calculation, it's being done over the data bits, right? Obviously, because that's what you're trying to protect in terms of errors. But it includes the parity bit itself and does not include the start and stop bits. So what this means is if you have odd parity, in order for there not to be an error, the number of 1 bits in the data and the parity have to be odd. Make sense? Now you might say, what's unusual about that? Well, to me it's counterintuitive, because if you have odd parity, what that means to me is if there's an odd number of bits in the data, then that bit should be 1. Right? That's what that means to me. Odd parity means if there's an odd number of bits, set the odd parity to 1. But that's actually, it's actually the reverse of that. It's not true. If you have odd parity, then the parity bit will be 1 if there's an even number of bits in the data. And when I say data, I mean just, the data contained within a single transaction, single transmission, right? In other words, if you look at the combined data bits and parity bits, if you have an odd parity, then that number should be odd, which means that basically what you're doing there is, as the transmitter, if I have an even number of 1 bits and I have odd parity, then I set the parity to 1, which guarantees that the combined bits are an odd number. Does that make sense? Okay, and then even is the other way around. So let me show you an example of that. So let's say I have, in the parity, I forgot to mention here too, the parity bit comes right after the data bits. So what you end up with is a start bit, data bits, parity, if parity is enabled, if you're using it, parity bit, and there's only 1 parity bit, and then 1 or more stop bits, right? So in this case, I have 9 data bits, even parity, and 1 stop bit. So that means that I have 9 data bits and then there's a start and stop bit. That brings the total number of bits to 11, right? And then I have a parity bit, which brings the total number of bits to 12, right? So that means that every time the channel becomes active, or when I say channel, I mean just remember that these two lines are independent of one another, right? Again, I'm showing this as, the way this is shown is a little misleading because it implies that the transmit and the receive are working together, that they're synchronized somehow, when in reality they're not synchronized, they're independent of one another. So you can send a transmission on, transmit without getting anything back. So it's bidirectional, but unlike SPI, the bidirectionality is managed independently on both sides, right? It's not like SPI where the MOSI and MISO work together, they're synchronized, right? You do an exchange. In the case of UART, they're not synchronized. I can send a couple things on transmit and then I can get a couple things back on receive, right? So they're not linked, they're not synchronized, right? But yet they're shown that way here just because this is a limitation of my software that I wrote that generates these timing diagrams, okay? But whenever I send something in this configuration, I have to send 12, the time it takes me to transmit is going to be 12 bit periods, right? Why? Because it's 9 data plus the start and stop brings me to 11 plus the parity is 12, right? So this is the difference then between baud rate and throughput. Baud rate refers to the bit times, how long each bit is on the channel. But that's not the same as the throughput of the data because of the overheads required by the start and stop and parity, right? So the throughput in this case is going to be the baud rate, but then you have to multiply that by 9, because 9 is the amount of data, divided by 12, which is the total size of each transaction. Now you might say, wait a second, wait a minute. Why would you pay the overhead of a start and stop and parity for each individual data word? Why not support multiple transactions like SPI does, where you have one start and then you can send multiple bytes, right? And then your parity and then the stop. Why not create a packet format, right? Why not do that? Well, they don't. I don't know. It doesn't work that way, right? So there's no way to do multiple, there's no way to do streaming. There's no way to encapsulate multiple words within one frame, right? Or one transaction with UART. So every single time you send anything, you have to put the start, stop, and optionally the parity around it. Does that make sense? So you pay the penalty, you pay the overhead, the control overhead, you pay that, the protocol overhead, you pay the protocol overhead individually for each word you send, right? Which is another weakness of UART, right? Because it should support, you would think it would have some way to batch together multiple words in order to minimize the amount of overhead, but it doesn't. So that's the reason why in the case of, no one talks about baud rate versus throughput for SPI. It never comes up. Why? Because SPI doesn't have any protocol overhead. But UART does, because you have to tack on extra bits for every single word you send, right? Does it make sense? Okay, so again, the baud rate is the native signaling rate of the channel, whereas the throughput is going to take into account the overhead. So in this case, the throughput is 9/12 the baud rate, right? Because again, you have to put the start and stop for each individual value you send across the channel. So anyway, okay, so then the parity, so what's going on here? So how do we do the parity calculation? Well, here's where things get tricky. Remember that the start and the stop are not included in the parity calculation. So, which seems strange to me, but that's how it works. You're only doing the data and the parity bit, which means that you have to, when you look at this, you have to skip that first cycle, skip it. That's the start bit. No one cares about the start bit. That just starts, right? Then you have to count the number of 1 bits, but don't include the stop bit. And keep in mind, there might be more than one stop bit. In this case, there's just one stop bit. So I need to count everything. I need to count all the 1 bits between the start and stop bit. So that would be 1, 2, 3, 4, 5, 6. So there's 6 1 bits, not including the start and the stop. And 6 is an even number, right? So it better be an even number because it's even parity. It's always going to be an even number, unless there's an error, right? Okay, well, in this case, that's the transmit. Let's look at the receive side. 1, 2, 3, 4, 5, and possibly 6? Possibly 6, yes.
So do we give it 6 since the parity bit's right?
Yeah, exactly. No, the parity bit's actually not 1 here. The parity bit's actually 0. But remember that the parity bit is not meant to indicate the parity. It's meant to manipulate the number of 1 bits to match whatever the parity is. Does that make sense? So it's not like, so you just, when you do this, you include the data and the parity together as one glob of data. You count the number of 1 bits, and it should be always even, right? So in this case, I've got 1, 2, 3, 4, 5. I'm only counting 5, but I don't know what this bit is, right? Well, obviously, I know what it is. It should be a 1, right? Because it can't be 0, right? Because if it was 0, it would violate the even parity, right? So this is an example of what's called an erasure, which is where there's an error, but I know what bit is an error, right? Now, the problem is, unfortunately, with UART, I don't think that's typically true. If there's an error on the channel, I don't think the receiver knows what bit is an error. The reason I'm doing it here is it's just an exercise, right, for you to be able to understand. This is just a kind of a manufactured question. But in reality, I don't think there's any erasures. There's just errors, meaning that the receiving side receives data, and then it has to figure out if there's an error. So the goal of parity is error detection, not error correction. If I knew what bit was an error, then I can correct it, right? Then I can do correction, but assuming there's at most 1, right? But you're not generally going to know in reality which bit is an error. You're just going to know if the parity calculation fails, in which case we have an error. And then what do? I don't know. I guess application specific, right? Okay. All right. So yeah, this just points out what's going on here. Start bit, data bits, parity bit, stop bit. So what's the challenge? If I ask you this on like a test or a quiz, the challenge is to count those bits and being careful not to include the start and the stop, which may be more than 2 bits if there's multiple stop bits, right? So that's the challenge here from your perspective, is figuring out which bits to count, essentially, for the parity calculation. Any questions about that? Okay. Here's an example. Assume a UART channel operates at baud rate 9600 BPS. So baud is measured in bits per second. Now, but keep in mind, though, that for the purpose of this hardware, the hardware cares more about the reciprocal of the baud rate. It cares about how long each bit slot is, right? How long of a time each bit has on the bus, right? Which is 1 over the baud rate. But typically, it's the number that you see as baud rate, which is bits per second, right? So 9600 BPS, 7 data bits, 1 parity bit, and 1 stop bit. What's its throughput? So in this case, you have to calculate the overhead, the protocol overhead, which is the total number of bits is 7 plus 1 plus 1 plus 1, right? 10. So there's 10 bits, 10 bit times. There's 10 bit slots that are occupied in order to transmit only 7 data bits. So there's the overhead is 3 bits out of 7 or 3 bits out of 10. Anyway, the idea is you take 7 over 10 is 70%. You get 70% max utilization of the channel for the data, and you'd multiply that by 9600 baud, and you have 6720 bits per second of throughput. Now, I don't know how often, so the only case that you're going to try to actually use all the throughput is if you're programming an Arduino or something, right? Usually you don't use all your throughput because, as I mentioned, UART's usually for like terminals, you're typing, right? So usually throughput is not a big deal unless you're doing some kind of a bulk data transfer, like when you download your code to the Arduino. which, again, it would be better to do that over SPI, but there's no way to put SPI on top of USB, so that's why UART. All right, so here's another question. What bit is missing? 5 data bits, odd parity, 2 stop bits. This one's tricky because you can get fooled very easily here because there's 2 stop bits. So I have to count the number of 1 bits starting from the second one. So 1, 2, 3, don't count those. So there's just 3, right? There's only 3 1 bits visible. One is unknown. The parity is odd, so that odd must be 0, right? Because there should be an odd number of 1 bits, right? And then in this case, I just sent a 0. I transmitted a 0, but then because it's odd parity, I had to actually set the parity bit high so I could make the total bits odd because the data was 0, right? There's no 1 bits in the data. Okay? And then in this case, the question is, keep in mind, again, that was an erasure. There's an erasure there where I knew where the error was potentially. In this case, I don't know if there's an error, and if there is an error, I don't know where it is. So in this case, I'm checking if there's an error. This is an error detection problem. In this case, only 1 stop bit, odd parity. Again, start at second bit, so pretty much just 1. There's 1 bit. Yeah, so that one's fine. This one has 1, 2, 3, 4. There's 4 1 bits set on the receive side, right? So that's no good, right? That shouldn't happen because it's odd parity. There's an even number of 1 bits. So there is an error. There's an error on this receive side. I don't know where the error is, though, and there's really not much I can do about it. I just know there's an error. Okay. All right. So let's. Any questions about UART? Okay. So let's talk about. Let's go back to SPI. So I mentioned this earlier. This idea of what happens if I have one master and multiple slaves in SPI. I mentioned that. It was a problem. We had an issue over here with this topology. This one was fine. This one had an issue because the meso, you had a bunch of mesos that were shorted to one net, one wire, right? They were all fanning in. They're all shorted together.
One thing to note here, I'm not 100% sure, but I think ArduPilot might support the multi-slave select thing.
Oh, okay.
Yeah, I'm not 100% sure on that, but I think I remember it being able to do that. And that's the only thing I've ever seen that can do it, but yeah.
Oh, that's cool. Okay, good. Okay, so yeah, ArduPilot is the software, drone software. Okay, so what is the problem with that? Okay, the issue is, so SPI and UART both use what's called a push-pull driver circuit. Driver being the circuit that actually injects zeros and ones to an output pin. The way that those work, fundamentally, a push-pull is where on each chip, the pad, the I/O pad, has essentially a CMOS inverter, right? Or it may not invert, it may just be a buffer, but in that case you have to have 2 inverters kind of connected in series, right? But the way I have it shown here is I have just an inverter, and an inverter, you guys, we covered this in 611, so you guys are familiar with this CMOS arrangement where basically there's 2 transistors. One of them is responsible for sending a 1 bit, and the other one's responsible for sending a 0 bit, right? And the way that works is that if you want to send a 1 bit, you basically pull up the wire, meaning that you make this transistor low impedance and you make this one high impedance, right? That's basically all that means. So, and then, obviously if you want to pull down, you want to send a 0, you activate the other transistor. So you're always turning one transistor off and the other one on, and you can, toggle those to send a 0 or 1. Okay, the problem is is if you have two of these drivers, buffers, whatever you want to call them, you have two of these circuits, if they're both connected to the same wire, which is happening for MISO in that shared bus arrangement, right? So I've got MISO on multiple slaves all driving that same wire. That's a problem because if one of those guys pulls up, and when I say guys, I mean chips. These are independent chips, right? These are different chips on a circuit board or a breadboard, right? If one of the chips pulls up, in other words, he wants to send a 1, and the other one pulls down, wants to send a 0, what ends up happening is that you have low impedance to VDD on one chip and low impedance to ground on the other chip. So what will end up happening is, let's say that there's a 1 ohm resistance, equivalent resistance for whenever one of the transistors is on. Whenever a transistor is on, in other words, it's on, and if it's on, resistance is 1 ohm. You'll end up with a series resistance of 2 ohms, right, between the power supply on one chip and the ground on another. Now, I mentioned that the grounds are shared. There's a common ground for SPI and UART, right? There's a common ground, and usually you have a common VDD here too. But what will end up happening is that you'll start dumping a lot of current. So you'll have this low impedance path from power and ground, but involving two different chips. This is the part that I think is kind of confusing, is that essentially you've created a short circuit here, but the short circuit is not inside of one chip. The short circuit is created from the participation of two separate chips. And so you'll end up sinking current. Current will start roaring out of this first chip that's trying to pull up, and it'll start sinking down into the chip that's trying to pull down, right? So for example, if you have a 1 ohm resistance, say this is a 5 volt VDD, you basically have 5 volts seeing a resistance of 2 ohms, right? Which means you're going to get 2.5 amps flowing through, right? Now, that may not necessarily blow up the chips because 2.5 amps is not a lot of current. Might be too much for the chips that you're using. But the bigger issue is not even that. The bigger issue is that the voltage of that wire is going to end up being halfway between 0 and VDD, right? Assuming that the on resistance of the PMOS and the NMOS are equal, which they're probably not. But if we assume they're equal, 1 ohm and 1 ohm, and there's a 5 volt signal, 5 volt VDD, then this guy is going to be 2.5 volts, which is in the forbidden zone, right? That's an undefined binary value, Boolean value. So that's no good. So in other words, you can't, if you have push-pull type drivers, they have to not be in conflict. However, there is a way to fix that. A lot of the chips support tri-state buffering here, where you have a push-pull interface, but you also have the ability to electronically disengage, right, to disconnect. And you guys have probably, we've talked about this a little bit, but you've probably noticed already that in the ESP32, the I/O pins are quite flexible, quite powerful. They support this tri-state buffering. In fact, the pins are all bidirectional. They can be set up as inputs or outputs. And so obviously there's a way to disengage, right? There's a way to basically cut these guys off if you don't want them on there. So in the case of that multi-SPI thing I was talking about earlier, what would end up happening, I believe, is these MISO connections, the chips would understand, hopefully, that when the slave select is not, they're not being selected, right, for the transaction, they would tri-state the MISO, right? They'd turn off their MISO, right? And and hopefully there's no misunderstandings, and hopefully there's only one slave select on at a time, right, in that case, because it would be very easy to cause some problems if the master just activated 2 slave selects and then multiple slaves activated their meso, which would put the meso in contention. Okay, so yeah, but so that's one way to do it. However, that's a lot of trouble to work all that out, to create push-pull drivers only to have tri-states. An easier approach to this that avoids this complexity is called an open drain interface. The idea with open drain is that instead of using a push-pull, instead of having the ability to pull up to VDD or pull down to ground, you only implement the pull down side, right? So you basically allow the output to be explicitly driven to 0, right, is one option. Or, you just don't do anything with it. Just let it float, right? So my options with open drain is, if I'm a driver, if I'm a chip, I can set a wire to 0, or I can just not set it at all, right? Now you might say, well, if you don't set it at all, it's going to be floating, right? That's no good. Well, the way that you deal with that is you put a resistor here, a pull-up resistor, which is usually around, I think, 10 kiloohms. Is that realistic? Yeah, 10 kiloohms or so. You put this pull-up resistor here. And so what will happen is if I'm not driving, if I'm not setting the output wire to anything, in other words, I don't activate that NMOS, then the state of the wire will actually be 1, right? Except not really 1, because there's a resistor. Resistors change the voltage, right? So one side of this resistor is 5 volts, but the other side's not going to be at 5 volts. It's going to be a little less, right? But that's not a big deal, because when these resistors are off, these NMOSs are off, the equivalent resistance is really high. It's like a mega ohm, right? So what ends up happening is, if this guy is off, it ends up creating a voltage divider. You guys remember voltage divider? You covered that in circuits. So you have a voltage divider where the output voltage is going to be it's going to be related to the bottom side resistance, which is a mega ohm, right, divided by bottom side plus top side, right? So because a mega ohm is so much higher than 10 kiloohms, the voltage here in this voltage divider is going to be pretty high, right? It's going to be almost 5 volts, right? But that only works if the ratio of these two guys is huge, right? So you got to make sure that these pull-down transistors, when they're off, have very high resistance. But the problem with that is if I then do what I'm meant to do with this open drain, which is to attach a whole bunch of chips to one wire, right? So if I have a whole bunch of chips and they're all connected to one wire, then something happens here. I end up with a lot of these off transistors. I end up with a lot of them in parallel. And you guys remember equivalent parallel resistors, right? So as if I add another mega ohm in parallel, which of course I would have, because the whole point of this is to have multiple drivers on one signal, right? That's the whole point. So obviously I'm going to have multiple chips connected to this. And even if they're not driving, even if they're not pulling down, they have a 1 mega ohm resistance, but there's a whole bunch of them in parallel, right? So the equivalent resistance from the wire down to ground starts to shrink the more of these things I put on the bus. So in this case, I have the equivalent resistance is 1 over 1 mega ohm plus 1 over 1 mega ohm, and then you take the inverse of that, which is 500 kiloohms, which is still quite a bit compared to 10 kiloohms. But you can see that the more devices I hang on this, the more the down part of the voltage divider will be, it'll reduce the down part, the downside of the voltage divider. And this on voltage is going to start to shrink, right? But as long as it stays above the threshold, there's going to be a minimum threshold voltage that's considered a 1, right? And so as long as that's high enough, then that's not a problem, right? But it will, your noise, you guys remember from 611, we talked about noise margin. The noise margin will reduce the more things I hang on this bus. So as cool as this is, it's not super scalable because once I have 100 things on this bus, it's going to start to get a little dicey, right? But in this case, it's okay because my equivalent resistance when these guys are off is 500 kiloohms. And that's assuming no one's sending anything out on the bus, right? Now, what happens if a guy does send something out? What happens if one of these pulls down, right? What happens there? Well, if I pull down, then I'm basically just creating a low impedance path to ground, right? Which is just another voltage divider, except now the ratio has changed dramatically. My upside resistance is 10 kiloohms and my downside is 1 ohm, right? So that's going to pull it down to 0 pretty well, right? And then the problem is just at that point, I just have a 10 kilo ohm resistor up to VDD. I'm going to start sinking current. I'm going to start sapping current from the power supply. But 10 kilo ohms is high enough that it's not a lot of, it's like microamps, right? So that's not a real big deal. It's not as good as a push-pull in terms of efficiency, but it's still not a significant amount of resistance, a current. So anyway, so that's the idea. So in this case, the voltage divider when neither one of these guys is pulling down is going to be 500 kilo ohms. So the voltage divider is 500 kilo ohms divided by 510 kilo ohms, right? And I would multiply that by 5 volts, so I get 4.9 volts. I get a 100 millivolt drop if no one's sending anything, but that's still considered a logic 1, right? So not a big deal. And then I have leakage current. I'm leaking current 5 volts over 510 kilo ohms. That's 10 microamps. It's not too bad, right? So I have some leakage there, but that's not too bad. That's if no one's sending anything. Now, let's say I want to send a 0 out of this guy. So I send a 0 out of this guy, so I pull him down. This guy is not pulling down. Okay, so now my voltage divider is 1 ohm divided by 10K, right? Or 10,001 technically, which is, basically 0. Except now my leakage current is, I've got 10 kilo ohms essentially between power and ground, right? So that's half of a milliamp. So that's 500 microamps that I'm going to suck if any of these guys decide to pull down to 0, right? So it's not as efficient as a push-pull in terms of power, energy, but it is more efficient in terms of the amount of hardware resources I have to put in because all I need is that one resistor and the pull down, 1 transistor per output, right? And it allows me to safely multiply drive a bus, a wire. You guys with me? So there's no potential of me releasing the magic smoke. It's just a little bit more power intensive. That's the trade-off. Okay, and then if I turn these guys both on, it's not devastating because even if I turn both of these on, I'm still essentially just have 10 kilo ohms between power and ground. Okay, any questions about that? All right, so I only have a minute left, so I'm just going to introduce how all this fits in. So the reason I talked about all this was because the next bus technology we're going to talk about is I2C. I2C is a fancy way to say IIC. And IIC is an acronym that stands for Inter-Integrated Circuit. This is standardized. This protocol is standardized. So unlike SPI that was very informally defined, you could hack it and change it, and the transaction protocol was arbitrary. With I2C, that is not the case. Super strict. I2C is very strict about how you use it. But it uses this open drain technology to allow I²C to be multi-slave and multi-master at the same time. So remember, SPI can have one master and possibly multiple slaves. I²C can have multiple of both, multiple masters and multiple slaves. So it's kind of like Ethernet in a way, where you can hang a bunch of things on it, and on Ethernet, you can claim, you can have any host grab mastership of the bus, right? So, but we'll talk about that in the next lecture, but it won't be until after Lab 1, okay? So make sure you come, I'll send an email out to remind you, but make sure you come to lab for the next lecture, for next class, rather. Thank you.